Welcome to our guide on GCSE learning and revision made simple. If you haven't yet, please subscribe to our channel to help us keep making more amazing GCSE content. Today's lesson focuses on changing sea levels. In this lesson, we're going to look at how coastlines change when sea levels rise, sea levels fall, or the land itself moves up and down. When people hear the phrase sea level change, they often assume it only means the sea rising because of climate change. That is important, but it is not the whole story. Sea level can change because the volume of water in the oceans changes. For example, during an ice age, lots of water is stored as ice on land, so global sea levels fall. When that ice melts, water returns to the oceans and sea levels rise. But coastlines can also change because the land moves. In some places, the land is rising. In others, it is sinking. So the sea might appear to rise or fall relative to the land, even if the actual amount of ocean water has not changed locally. Today, we will look at two key types of sea level change: eustatic change and isostatic change. We will also look at the landforms created by changing coastlines, including raised beaches, rias, and fjords. The big question for today is the sea moving, the land moving, or both? Let's begin with our learning intentions. By the end of this lesson, you should be able to do three main things. First, you should be able to distinguish between eustatic and isostatic change. Eustatic change is a global change in sea level caused by a change in the volume of water in the oceans. Isostatic change is a local change in land level, where the land rises or sinks relative to the sea. Second, you should be able to explain how the last ice age shaped the UK. During the last ice age, thick ice sheets covered large parts of northern Britain. The weight of this ice pushed the land down. Since the ice melted, some of that land has been slowly rising again. Third, you should be able to identify landforms created by shifting coastlines. These include emergent landforms, such as raised beaches, and submergent landforms, such as rias and fjords. So today's lesson is about understanding how changes in land and sea combine to reshape coastlines over time. Before we focus on sea levels, let's quickly recap depositional landforms from the previous lesson. Deposition happens when waves lose energy and can no longer carry their load. On the coast, sediment is moved by processes such as longshore drift. Longshore drift transports material along the coastline in a zigzag pattern, following the direction of the prevailing wind and swash. Depositional landforms, such as spits and bars, are dynamic. That means they change over time as sediment is moved, deposited, eroded, and reshaped. A spit is a ridge of sand or shingle that extends out from the coast into the sea or across a river mouth. These landforms remind us that coastlines are never fixed. They are constantly changing because of waves, tides, currents, sediment movement, and sea level change. Today, we are adding another layer to that understanding. What happens when the coastline itself shifts because sea level or land level changes? Let's start with a quick sequencing task. You need to order the stages of spit formation from start to finish. The stages are: longshore drift moves sediment along the coastline. A hooked end forms due to changes in wind direction. The coastline changes direction, for example at a river mouth. Sediment is deposited in the sheltered water behind the headland. Take a moment to think about the correct order. Remember, longshore drift is the process that moves sediment along the coast. A spit usually begins where the coastline suddenly changes direction, but longshore drift continues to move sediment forward. The correct order is: first, longshore drift moves sediment along the coastline. Second, the coastline changes direction, for example at a river mouth. Third, sediment is deposited in the sheltered water behind the headland. Fourth, a hooked end forms due to changes in wind direction. This is a useful recap because it reminds us that coastal landforms are shaped by sediment movement and changing energy levels. But today we are going to focus on larger scale changes. What happens when the position of the coastline changes because sea level rises, sea level falls, or the land itself moves? Now let's think about the big question. The slide says, if you stood on the British coast 20,000 years ago, the sea would be 120 meters lower than today. That is a huge difference. If sea level was 120 meters lower, the coastline would not have been where it is today. Large areas that are now underwater would have been dry land. This raises an important question. Why does the sea move? Or is it actually the land that is moving? The answer is that both can happen. Sometimes the global sea level changes because water is added to or removed from the oceans. This is eustatic change. Sometimes the land rises or sinks relative to the sea. This is isostatic change. To understand coastal landscapes properly, we need to know the difference between these two types of change. Now let's master the key vocabulary. The first word is eustatic. Eustatic sea level change is a global change in sea level caused by a change in the volume of water in the oceans. For example, if ice sheets melt and add water to the oceans, global sea levels rise. That is eustatic sea level rise. The second word is isostatic. Isostatic change is a local change in land level. The land rises or falls relative to the sea. For example, land that was once weighed down by ice may slowly rise after the ice melts. This is called isostatic rebound or isostatic recovery. The third word is ria. A ria is a submerged river valley. It forms when rising sea levels flood a river valley. The fourth word is fjord. A fjord is a submerged glacial valley. It usually has steep sides and a deep basin because it was carved by ice. These four terms are central to today's lesson. Now let's compare eustatic and isostatic change more clearly. Eustatic change is global. During an ice age, large amounts of water are stored as ice in glaciers and ice sheets. Because that water is taken out of the oceans and stored on land as ice, global sea levels fall. When the climate warms and the ice melts, water flows back into the oceans. This causes global sea levels to rise. So eustatic change is about the amount of water in the oceans. Isostatic change is local. This is about the land rising or falling. The slide gives us a useful image. Think of the Earth's crust like a seesaw. During the last ice age, heavy ice sheets pushed northern Britain down. When the ice melted, that huge weight was removed. Since then, the land has slowly been springing back up. This is isostatic recovery. So the simple difference is, eustatic change equals sea level changes globally. Isostatic change equals land level changes locally. Now let's apply this to the UK. During the Devonian glaciation, which was the last ice age, ice sheets reached as far south as Norfolk. These ice sheets were extremely heavy. Their weight compressed the land underneath them, especially in northern Britain. When the climate warmed and the ice melted, the weight was removed. As a result, northern Britain began to slowly rise again. This is called isostatic recovery or isostatic rebound. Today, Scotland is still rising, but the process is not the same everywhere. As the north rises, parts of southern and southeastern England are slowly sinking relative to sea level. This means the UK is tilting like a seesaw, north up, south down. This matters because sea level rise does not affect every part of the UK coastline in exactly the same way. In places where land is sinking and global sea levels are rising, the risk is greater. Now let's look at emergent landforms. Emergent landforms are features that show where land has risen relative to the sea or where sea level has fallen. One important example is a raised beach. A raised beach is an old beach found above the current sea level. It may be found high and dry, away from the present shoreline. Raised beaches form when the land rises faster than the sea, often because of isostatic rebound after an ice age. Imagine a beach forming at sea level. Waves deposit sand and shingle along the coast. Later, the land rises. The old beach is lifted above the reach of the waves. Over time, a new beach may form at the current sea level, while the old raised beach remains inland or higher up. Raised beaches may be found with old cliffs, wave-cut platforms, and sea caves far back from the modern coastline. These landforms are evidence that the relationship between land and sea has changed. Now let's test your understanding. The statement says, a raised beach is caused by a global drop in sea level only. Is that true or false? Take a moment to think. A global drop in sea level could expose old coastal features. But is that the only possible cause? Remember, raised beaches are often linked to land rising because of isostatic rebound. So should we say raised beaches are caused only by eustatic sea level fall, or can isostatic land movement also be involved? The statement is false. A raised beach is not caused by a global drop in sea level only. It is often caused by isostatic rebound, where the land rises relative to the sea. The correct explanation is, it is primarily caused by isostatic rebound, where the land rises up out of the sea. This is why raised beaches are called emergent landforms. They show that land that was once at sea level has emerged above the present shoreline. Option B is incorrect because destructive waves do not push sand higher and higher up a cliff face to form a raised beach. Raised beaches are linked to relative sea level change. The correct answer is A. It is primarily caused by isostatic rebound, where the land rises up out of the sea. This is a key distinction. If sea level falls globally, that is eustatic change. If land rises locally, that is isostatic change. Both can affect the position of the coastline, but raised beaches in places such as parts of Scotland are strongly linked to isostatic recovery after the last ice age. So remember, raised beaches are emergent landforms. They form when land rises relative to the sea, leaving old coastal features above the current shoreline. Now let's look at the opposite situation, submergent landforms. Submergent landforms form when sea level rises relative to the land. This may happen because global sea levels rise, or because the land sinks. When sea level rises, it can flood existing valleys. Two important submergent landforms are rias and fjords. A ria is a drowned river valley. It forms when rising sea levels flood the lower part of a river valley. Rias often have winding shapes because river valleys usually meander. They also usually become deeper towards the sea. A fjord is a drowned glacial valley. It forms when sea level rises and floods a valley that was carved by a glacier. Because glaciers carve deep U-shaped valleys with steep sides, fjords are often deep, narrow, and steep-sided. So both rias and fjords are flooded valleys, but they have different origins. Rias come from river valleys. Fjords come from glacial valleys. Rias and fjords may look similar because both are flooded valleys, but their origins are different. A ria follows the winding path of a river valley. Rivers usually erode around bends and create more irregular, branching valley shapes. So when sea level rises and floods a river valley, the resulting ria often has a winding outline. The slide gives the Fal estuary in Cornwall as a classic example of a ria. A fjord is different. Fjords are carved by glaciers, not rivers. Glaciers are extremely powerful and can cut deep, straight troughs through rock. This means fjords are often straighter, deeper, and steeper-sided than rias. The slide gives Milford Sound in New Zealand as a famous fjord. So the key comparison is, rias are drowned river valleys, usually winding. Fjords are drowned glacial valleys, usually deep, steep-sided, and straighter. Now let's apply this to future risk. The question is, if the southeast of England is sinking isostatically while global eustatic sea levels are rising due to climate change, what does this mean for cities like London? This is a really important question because it combines two processes. First, global eustatic sea level is rising as oceans warm and land ice melts. Second, parts of southeast England are sinking relative to the sea because of isostatic adjustment. That means London faces a double threat: rising water and sinking land. This increases the risk of flooding, especially from storm surges. A storm surge happens when low pressure and strong winds push seawater inland. If this happens at high tide, and sea levels are already higher, the danger is greater. This is why London needs major flood defenses such as the Thames Barrier. But as sea levels continue to rise, these defenses may need upgrading or replacing. In the long term, some low-lying inhabited land may become much harder or more expensive to protect. You might have said that London faces a double threat: sinking land and rising water. That is correct. You might also have said that this increases the risk of flooding from storm surges. That is also correct. If the sea is rising globally and the land is sinking locally, relative sea level rise becomes more serious. This means flood defenses, such as the Thames Barrier, may need constant upgrading. A strong GCSE answer might say, London is at increasing risk because global eustatic sea levels are rising due to climate change, while southeast England is slowly sinking because of isostatic adjustment. This means relative sea level is rising faster. As a result, storm surges and high tides could cause more frequent flooding. Expensive flood defenses, such as the Thames Barrier, may need to be upgraded to protect homes, businesses, and infrastructure. That answer is strong because it links eustatic change, isostatic change, and flood risk. Let's finish by summarizing today's lesson. Sea level change can happen in two main ways. Eustatic change is a global change in sea level caused by a change in the volume of water in the oceans. During an ice age, water is stored as ice on land, so sea levels fall. When ice melts, water returns to the oceans and sea levels rise. Isostatic change is a local change in land level. During the last ice age, heavy ice sheets pushed parts of Britain down. Since the ice melted, northern Britain has been slowly rising through isostatic recovery, while parts of southeast England are sinking relative to sea level. We also looked at landforms created by changing sea levels. Emergent landforms form when land rises relative to the sea. A raised beach is an example. Submergent landforms form when sea level rises relative to the land. Rias and fjords are examples. A ria is a drowned river valley. A fjord is a drowned glacial valley. The key idea from today is coastlines change because both the sea and the land can move. Understanding eustatic and isostatic change helps us predict how coasts may respond to future climate change. Thank you for watching. If you found this content helpful, please remember to like the video and subscribe to our channel. It really helps us continue creating valuable content for you. Thanks for watching.